So to talk about Lewis structures, Lewis diagrams, and Lewis dots, and all the different things that Lewis had come up with, we have to first talk about what valence electrons are in our case. We kind of talked about them at the end of the last lesson. They are the outside electrons, not the core electrons. And as far as like compounds are concerned, valence electrons are the reactable electrons. So that's like my quotes word because it's not like a real word. Reactable electrons. Now I'm going to put that in like a heavy quote here because I don't think that's a real grammatically correct sentence, but I think it's the one that makes the most sense. These are the ones that are going to do chemical reactions. These are the ones that are going to bond with other atoms. They're the ones that are going to share or trade or transfer electrons in some kind of chemical reaction. The core ones don't do that. And basically the way we can set this up is that noble gases have no valence electrons. No valence electrons. Because they're not reactive. They don't do anything. Now, we can make compounds with them if we force them to. Now, the ones we can make do stuff are xenon and radon, the really, really big ones. They have so many electrons, you can mess with them a little bit. But the little ones, neon and helium and argon, they do nothing. They're almost completely inert. It doesn't matter what we force them into. They end up doing nothing. We can force xenon and radon into do things, but we can't do anything else. Not reactive. That's supposed to say reactive. Good job. React. There's a C in there somewhere. Reactive. That's a much better spelling of that word. Hopefully you guys did it right and didn't have to look at me. Okay, sodium and fluorine are some of the most reactive. They have valence electrons. Electrons. And are reactive. They do things. You can put different compounds with sodium and fluorine. Some of the great ones. Oh, we're fast today. Thank you very much, sir. Some days it's like 1:45 before it comes. Yeah, that's good. Okay, so we're going to look at mostly not transition metals for this particular section. We're not going to get into them because, as we said before, they get weird. So for the beginning, we're going to skip past them. So we're going to look at the third period and go across third. That's the fourth. But either way, that's actually the fourth period. I don't know why that says that. That's the fourth. Row 4 starts with potassium. But either way, we're skipping the transition metals because all those ugly ones in the middle follow different rules anyways. So we're just going to skip the middles. And we can count our valence electrons kind of looking like this. And they go up by row. So potassium, 1 past argon, has 1 valence electron. And calcium is going to have 2 valence electrons. And remember, skipping all the transition metals. We're skipping scandium, titanium, vanadium, and all those other fun ones. Going right to gallium, which has 3. We figured this out yesterday. At the end of yesterday's lesson, we did gallium as an example. And we found it had 3 valence electrons. It had 2 in the S's and 1 in the P's. And so we can keep counting basically, 4, 5, 6, 7. And we don't write 8 valence electrons because krypton is a noble gas and 8 is what we call full. We say it has none because it basically goes back to being full to being charged. And so krypton we're going to take a look at, looks like row 2, a nice easy row, and try to fill up the electrons. How many electrons does a lithium have in its valence shell? 1 electron. So this is very exciting. 1 electron. And then we can look at beryllium. It's going to have 2, and we go around the circle like this. It doesn't matter which direction you go around, but you start at one place. I like to start at the top just as convention. It doesn't matter where you start as long as you go around, and we almost always go clockwise. It doesn't actually matter as long as you're filling an empty orbital. Boron is next. It has 1, 2, 3, and so those are separate there. Carbon, which we all remember from organic chemistry class, actually has 4. Right? 4 empty ones, right? 4 singles going around it. This is another help explanation why carbon likes to form 4 bonds. This is where. So this is a lot of like relating to the previous things we know in this chapter. We're kind of connecting them back and hopefully part of the, what's it called? Part of the review process for our end of year stuff. Okay, nitrogen has how many valence electrons? No, it does not have 3. It has 5. It has 5 valence electrons. It has 1 here, 2 here, 3 here, 4 here, and 5 here. So we have all the 4 got used up, all the 4 orbitals got used up once, and the last electron had to go into a pair. So we have one of the orbitals now has 2 in it, and the other 3 have 1 in them. Same thing with oxygen. How many electrons do we have to deal with oxygen? 1 more, 6. So we're going up by 1 each time. We're just going all the way across the rows. So 1, oops, I didn't do it the right way in the order this time. I was looking at the answer. And so we go all the way around with the 4 and then fill up what's left over. So we have 2 pairs and 2 singles with oxygen. That's the shape of oxygen. 2 pairs and 2 singles. That's what matters. And usually, I want to point out here that the pairs like to be together and the singles will be on the same side. So instead of having, say, 2 pairs like that are across, they usually are more on like they're together because you would go in a circle basically. So wherever they're together around the circle, as long as it goes pair, pair, single, single at some point around the circle. Fluorine has 7 valence electrons, so we got to put all 7 dots in here. Oops, excuse me, leaned on the page. Back to the part where we see. We're going to go dot there, dot there. We're going to do it in the right order, and then start pairing up, start pairing up, start pairing up. So fluorine has 3 pairs and 1 single. Neon has 8 electrons in this row, so it's just going to be all full, all the way around full to show this steps. Now those blanks below, I didn't put a label on it because this is just a picture out of your textbook. But these blanks below, I'm going to give a different description. This is what we call a combining capacity. And basically, it's a how many bonds can this thing form? How many things can it interact with? How many things can a single lithium interact with? Any guesses? It's 1. It can only do one thing. Only this electron can do anything. It's got 1 hand to hold. It can't do anything else. Any guesses for beryllium? 2. And so on. We get 2, 3, and 4. These are our normal ones. We're going up in these numbers. Number of different partners these kinds of elements can have. The number of different bonding styles they can have. Now, nitrogen starts messing with it because the singles are the ones that like to do stuff. As we found before, pairs are reasonably stable. So pairs are happy to stay pairs. So nitrogen actually has a combining capacity of 3. It likes to form 3 bonds. Oxygen only has 2 empty pairs, so it has a combining capacity of 2. So on, fluorine has 1. And neon, very conveniently, has none. Neon wants no partners. It wants no business from anyone else. So that's called a combining capacity. So this is going to take the rest of it, basically, is now we're going to talk about the Lewis structures of molecules. So when electrons get paired in an orbital, they don't form bonds between atoms. They're called something called lone pairs. Now, I didn't make any blanks over here because I forgot. They're called lone pairs, and they're called lone pairs because they hang out by themselves. They don't do anything in chemical terms. They are part of space, so they take up geometry space, but they don't take up a bonding site. When 2 electrons are shared, they are drawn as a line. That's a bond. My example that I'm going to show you guys on how to do these things is called ammonia. What's our formula for ammonia? You guys don't know what ammonia is yet? That's the one. It's NH3. So we're going to draw a Lewis structure of ammonia to try to see how ammonia fits together. So we're going to draw each of the elements by themselves. We're going to do the whole process here as part of the example. And you're going to start seeing the patterns and be able to make shortcuts soon. But we're going to draw them all together here. So I'm going to draw my hydrogens. How many valence electrons does a hydrogen have? 1. It only has 1 electron, so it's all valence all the time. How many hydrogens do I have? 3 hydrogens. So I'm just going to draw them each individually here, kind of like this. So I've got 3 hydrogens, and then I also have a nitrogen. I should have put the nitrogen over here. And we drew the nitrogen on the previous page. So we're just going to draw in the dots for nitrogen. Now, this is my other point to point out. Don't draw dots with your pencil like tap. Draw like dots like you mean it. Like I don't want to see little taps like this. I want to see dot here, dot there, dot there, dot there, dot there. Like, make a dot like you see them, right? Don't like a little pencil, little tap, because you're going to miss them. They're going to get missed. So when we make our structures, we basically need to account for all of the electrons that we have. How many electrons does this compound bring to the table? How many electrons does the hydrogens bring? 3. How many electrons does the nitrogen bring? 5. So I have a total of 8 electrons that need to be in this diagram. So when I do the diagram down below, I need to be able to count 8 electrons, or I haven't done my diagram right. All the electrons before have to equal all the electrons after. All right. And usually you can start by assigning which one goes in the middle. It's pretty obvious in this one. The single element goes in the middle. It's pretty easy. So we're going to put nitrogen in the middle. And I know I have to put hydrogens around it. So I'm just going to draw them around them in this kind of space like this. So those are my 3 hydrogens. It doesn't matter which arrangement you want to put them in, but we can put them here. And we know we need at least a bond between each of them. So I'm going to draw a line here, here, and here. Now, how many electrons does a bond take up? Yeah, how many electrons does it take to bond? 2. 2 electrons takes to bond, right? 2 electrons are shared between an atom. That counts for 2. So every time we draw a line in a Lewis diagram, that counts as 2 electrons. How many electrons have I used up? I've used up 6. I have 3 bonding ones, and there's 3 bonding. So 2 and 2 and 2. So I have 2 electrons here, 2 electrons here, and 2 electrons here. That's a total of 6. How many leftovers do I have? I have 2 left, and I usually like to put them to fill up the extra spaces. So nitrogen has an extra space here. It has an empty orbital up here. So we're going to put nitrogen, it's going to give 2 dots over here. So now I've accounted for all of the electrons in this diagram. I have all 8 electrons accounted for. Another way of looking at this is one way of doing it, just by adding. We can do it by connecting. The single dots really want to hold someone's hand. They do not like being singles. A single electron is also known as a radical in chemistry terms. They are very, very unstable. They are not happy. So electrons will try to make pairs. Pairs are happy. So basically, this single electron is going to want to grab that single electron. This electron is going to want to grab that one. And this one's going to want to grab that one. And so that's kind of showing where those bonds are going to show up. And it also shows that this extra one exists at the end. So there's another way of thinking about this. Another even more important rule is that for most elements that we're going to look at, they follow something called an octet rule. Now, it's a rule, and I'm going to put it in here because it's a rule is only as good as it works. There are examples where the rule doesn't work. But it works for most things. It's a good starting point and seeing where the exceptions go after that. So it's a starting point with that. And so the goal is to get 8 electrons in their valence shell. So they form bonds to try to fill up their extra shells, right? Because they want that S2P6 kind of arrangement around their nucleus, because that allows them to be stable. 8 is stable. So what we can do is we can then do like a kind of after analysis to take a look at and see, are each of the atoms full? And we do that by taking each center and looking at what's around it. So I'm going to do a little bit of drawing here. It's going to look a little silly for a second here. But we're going to look at the nitrogen. And I'm just going to draw a circle around the nitrogen kind of like this. And around the nitrogen, we're going to see, count up all the electrons that are with the nitrogen itself. So I'm looking at, I've got 2 from the pair, 2 from this bond, 2 from this bond, and 2 from this bond. That adds up to 8, right? So we're looking at, there's 8 on each of those. So it's going to look a little busy here because we're doing this all like overlapping structures to try to explain where all of these go. So the nitrogen, what I quote, sees 8 electrons. It has the pair and 3 bonds. That adds up to 8. Now, hydrogen is a notable exception. If I look at all the electrons around the hydrogen, how many does it see? It only sees 2. Is 2 8? 2 isn't 8. But if you look at where hydrogen is on the table, 2 is full for hydrogen. Hydrogen is in the first row with only 2 elements, so 2 is full. So hydrogen's full only has 2 electrons. So even though the hydrogens only have 2 electrons, 2 is full for hydrogen, right? 2 is full here for hydrogen. So for hydrogen having 2, that's a happy hydrogen, right? Nitrogen having 8, that's a happy nitrogen. So those are basically the main points for our Lewis diagrams. Now I have 6 here to show us. We're going to go through them together. They are very different, each one, and so they're going to follow a different rule. So we're going to go nice and slowly through each of them. Hopefully they make some sense. All right, we're going to do water. It's a very common example. We got to figure out where water's going to go. So the first thing I want to do is I want to count up all the electrons that water is bringing to the table. So how many does each hydrogen bring? 1. And how many does each oxygen bring? Oxygen does not have 2. How many valence electrons does oxygen have? It has 6. We can look at the previous page. Oxygen has 6. And so how many electrons? There's 2 from hydrogen plus 6. So we have another total of 8 electrons to work with here. I don't know why that was in red, but that's fine. Which one are we going to put in the middle? We're going to put oxygen in the middle because that way I can put a hydrogen on each side. So, what? Why is it so loud? So we're going to put oxygen in the middle. And remember the way we drew oxygen with its pairs on each side and its singles on the same side? Water, which we've seen 100 times, is a bent molecule. So we know it's going to be in this orientation. So we know water is going to be kind of like this. And now we've got to figure out how many electrons we have left. So how many electrons have I used up just by connecting these elements? I've used up 4 electrons because I've got 2 bonds here, so I've used up 4. How many left do I have? I got 4 left. So where should they go? Is hydrogen full? Does hydrogen see 2 electrons? Yes. Each of the hydrogens already sees 2 electrons. So a hydrogen here has a bond to it, so it sees 2 electrons. Hydrogen is full at 2. Hydrogen is full at 2. Is oxygen full? No, oxygen only has 4 electrons. 2 from here, 2 from here. It wants 8. So I can put the extra 2 on here. And we put them on in pairs. We put 2 here and 2 here. So that gets us, I can see that, I'm not going to draw all of them, but I can see that that is 8 electrons there. So there's 8 electrons around this oxygen, so it's a happy oxygen with 8 electrons around it. So that's why water, in this case, is a very stable molecule. It has hydrogens are happy, the oxygens are happy, everything is happy here. We can do the same thing. We're going to go to carbon dioxide. It's going to be a little different. How many electrons does carbon bring to the table? Carbon brings 4. 1 carbon, each they bring 4. How many does each of the oxygen bring? They each bring 6. So I have 6 and 6. Altogether, that's 16 electrons. So in this case, I have 16 electrons to work with. A lot more. Which element should go in the middle? Carbon in the middle. The one that singles is going to go in the middle. So I'm going to draw it kind of like this. Carbon on one side, oxygen on one side, oxygen on the other side. We know we're going to have, there's got to be at least one bond holding each other on, right? They have to be attached in some way. So we got to have at least this many bonds. How many electrons have we used up now? We've only used up 4, so we still got 12 left. That's a lot of electrons left. How many can I put around each oxygen? At most 8. So that's not going to give me enough. How many does the carbon see? It only sees 4. How many does the carbon want to see? It wants to see 8. So we can add more than one bond on each side to allow these things to match. So we can have carbon, which likes double bonds. We know this from organic chemistry. We know carbon likes double bonds. And now we can see, okay, carbon now sees a full 8, right? If I look, I can see carbon has 8 electrons here, right? It's got 8 electrons. Does each oxygen have 8 electrons around it? No, it doesn't, right? So are there extra electrons for us to give to oxygen? Have we used up? How many have we used up now? We have used up 8, so we still have 8 left. So we can give each oxygen 4, right? We can give each oxygen 4 more dots. I can put dots here, I can put dots there, I can put dots here, I can put dots there. And now I can look and see this oxygen has 8. This oxygen has 8. So that's 8 electrons there, 8 electrons there, 8 electrons there. So in this case, carbon has double bonds on each side. Okay. So for the nitrogen, we have basically 5 plus 5 is equal to 10 electrons for a nitrogen. Let's go back to this right color. So I'm going to draw 2 nitrogens separately, but hopefully in an orientation that makes sense. So I'm going to draw this here, like the nitrogen kind of shaped like this. And then I'm going to draw the other nitrogen like this. Because hopefully that makes what's next going to make sense. So each of these nitrogens is true, right? I have one nitrogen and another nitrogen. You may have seen this before, but remember, each one of the singles doesn't want to be single, it wants to grab a partner. So each of these is going to want to join up with another one. So we're going to have 3 of these bonding pairs created out of this arrangement. So each of those ones that go together are going to become a bond, and then we have 2 left over on each side not doing anything. So our Lewis diagram here is going to look like this. 1, 2, 3 in the middle with 2 kind of over here. Now, you could put them on top, but better would be as far away from the other electrons as possible. Electrons do not like each other unless they're pairs, which we won't get into why the pairs work. They just do. Having these pairs as far away from all these electrons in the middle is good. So it's good to keep those pairs away from each other. Okay. Right? We got 5 fluorines, but how many orbitals do we normally have? 4, right? So we got to somehow fit 5 fluorines around this one. So we have an expanded octet. So this is one of the ones that is my rules that break, usually due to things being bigger. The bigger they are, the more likely they are to break rules because they just got way more electrons to play with. We're not going to get into why, it just is. How many electrons does a phosphorus bring to us? Where does phosphorus give us electrons? 5. Gets us 5. How many does fluorine give us? What does fluorine give us? How many electrons does a fluorine grab? 7, right? Each fluorine has 7 electrons. So I have this silly thing, 3 times 5. I'm just going to write it like that. So that's a total of 40 electrons. 7, yeah. Start writing bad math. 3 times 7, so that's 40. 5. What am I doing here? What have I done? I'm all... Back to the proper ones. Okay, it is 5 fluorines. Each of them have 7. I knew the answer was 40. I did it before, so I knew the math was right. Just apparently forgot how to write. Okay. That's fine now. We have 40 electrons to play with. But we know that we're going to need to get 5 fluorines stuck to the center of phosphorus. So this is one of the ones that starts messing with our rules. So let's draw it the only way that's left. We put a phosphorus in the middle, and we draw 5 different fluorines around each side. As far apart as we can. In this case, Lewis diagrams are 2-dimensional. So there is a 3-dimensional arrangement of that. We'll get to those. But for now, this is a fine arrangement. And now we just have to make sure we account for all the electrons. So how many electrons have I used up? I've used up 10, right? How many left do I have? I have 30 electrons left. Where can I put them? I could put on double bonds, but if I look at fluorine from the previous page, how many bonds does fluorine like? Just wants 1, right? Fluorine only likes 1 bond. It has a combining capacity of just 1. So fluorine's going to want a lot of pairs on them, right? It wants a lot of pairs. So how many fluorines? I got 5 fluorines. How many extra electrons can I put on each fluorine? I can put 6 on each fluorine. I can put 2 here, 2 here, and 2 here. So that's 6 extra fluorines, or 6 extra electrons per fluorine. Will that get me up to 30 if I do that on each one? Is 6 times 5 30? Yes. Yes, it is. So we can put each of these fluorines is going to have a lot of dots on it. So each of the fluorines has 6 electrons around each it. And we try to space them around as best we can. 3 pairs to keep our diagram as clear as we can. Okay, so I think I got that sorted. So at the end, we've got 6 around each fluorine plus the 5 bonding pairs. That's 10, so 30 plus 10 is 40. We have all the electrons sorted. Now, in this case, we have phosphorus is a new word. It has, how many electrons are around this phosphorus now? 10. Is that normal? No, right? It's still fine, but it's not sort of our normal things. It has a word called hypervalent. So that's too many electrons, right? Hyper means too much, and so hypervalent means too many electrons. So it is the only way for this compound to exist, and when put in 3 dimensions, it works. Rules are only rules as much as they describe reality. You can put fluorines around phosphorus like this, and so it does work. So the octet rule is really hard and fast, but only for that second row. everything lower than second row, it's kind of more like guidelines. It's better if it's 8, but if it's 10, that's not terrible. Okay. This is a weird one. We're going to have a little bit of mess here. So this is something O3 is a real molecule. Do you guys know what the name of O3 is? It's ozone. Ozone. You know, the layer that stops all the UV from burning us. Right. So, how many electrons does each oxygen bring to the table? So that's 6 each. So I got 18 electrons to work with here. So, oxygen, just like the one in the water, is going to be bent. So we're going to start with drawing a bent molecule. So I got oxygen here. It's going to be an oxygen here. So going to be an oxygen here. Okay, so we got this many here. It's going to be a little bit weird. So I know I'm going to need 3 bonds to make this work. So I need an extra bond somewhere. So this is going to get a little silly. I'm going to need a bond here. And where can I put the extra electrons? I got to put 2 here, 2 here, or 4 here, and then all 6 here. So this is a way for it to get all of my electrons laid out. But I put the double bond on the left side. Why didn't I put it on the right side? The answer is, it doesn't matter. It's actually both. This is something called a resonance structure. So it's exactly the same forward and backwards. Where did we otherwise see resonance structures? Guys, remember organic chemistry, resonance structures? Apparently not. This is the benzene rings of organic chemistry where they share the electrons a little bit before, a little bit after. So this is one way of drawing it. This is called resonance. And so that's where we get our back and forths there. So this is actually both this way and forward, but just like the resonance in the benzene, this ends up being a symmetrical molecule where it's basically, it works out to being like a 1.5 bond on each side. So this is one way of drawing it where it's a double bond one way mixed with a double bond the other way. It's like sometimes one or the other, but this is how these work out. This is how ozone works out. So this resonance structure between 2 different things. Okay. So I want each element to C8, right? We want each thing to C8. How many does the double bonded oxygen have? It sees 4, so it only wants 2 more. Each of the single bonded O's wants 6 more. So each of those is going to get the 6 more. So we basically can follow the pattern the rest of the way through. So many dots. But each single is going to get 6. And each double is going to get 2. So each structure does have, oops, almost done. Now I'm done. Each one has the 2.